Now, hello, good morning, good evening, good afternoon, everybody, wherever you might be. Today we have ŁUKASZ KACZMARCZYK from the University of Warsaw. He is a PhD student of Tomek Maszczyk, and he will report on his joint work with him, which is on information geometry of Bayesian, updating and replication. Part one, classical setting. It's all yours. Take it away.
Thank you very much. First of all, I'd like to say that it's a great honor for me to talk on Wednesday and not on Friday as usual. And I know this topic is a bit unorthodox for this seminar, but I hope during the talk everyone will see at least a few connections with non-commutative world in this work. So, okay, first of all, let me say a few words about what's this all about. Well, our main goal in this work is to build what we call an epistemic machine, which will formalize the intuitive process of gaining and losing information, which would incorporate into itself the Bayesian updating, the data replication, and the synergy between the loss of information and the reproduction of it will be due to James' principle, which is famous from statistical mechanics. So first we will start with, I think, about 15 to 20 minutes of motivation and formulation of the problem, and then we'll play around with a bit of formal constructions. First, theory on probabilistic side, then we'll jump to convex geometry, and at the very end, I'll say a few words about possible further generalizations of what we'll see. So, okay, first things first, we will be talking about statistics, mainly, as headline says, from probability to convexity, which simply means that inside of what in some circles is standard, we will not look at the random variable as a measurable map between measurable spaces, but we will always take as a codomain a convex set, and moreover, we will identify the measurable map f with the function of taking the integral with respect to of f with respect to a probability distribution, and this is a well-posed approach thanks to this diagram, simply because we have this delta, which takes the elementary events from the space omega and assigns to it the atomic measure, and this will be our universal random variable, simply because given any other random variable on this space, we can uniquely extend it to be defined not on the space omega, but on the space of all probability measures on the sigma field that is paired up with omega, but we would mostly think about it as all the probability measures on omega. And because of that, we can exchange measurable maps between measurable spaces for affine maps between convex spaces, because all the probability measures are a convex set. Second of all, this way of looking is quite nice, given a relation between random variable f and G that we shall call domination, in this context that F dominates G, which is defined by the property that if for two probability distributions P and Q, F has the same expected values, then G also has the same expected values. Then if F and G are in the domination relation, it is equivalent to the fact that the space of all possible expected values of F and all possible expected values of Y are related by an affine map. So this exchange of measurable random variable as measurable map to a random variable as an affine map is well behaved.
So what do you mean by affine map?
It's quite literally an affine map, because for X and Y,
They are spaces.
they are convex sets, and they inherit, they can be embedded into the affine space, and then the affine maps can map one into the other. So they are the plain old affine map, nothing special. Okay, so thanks to that, from now on, we will identify F with this affine map. So don't be confused that you stop seeing this one. It will be simply overlapped with just F. And we can now consider this generalized process of taking expected values, because formally only this first one is taking expected value with respect to measure directly at any of these stages. We can also look at it like that by simply composing all these arrows around here, but each step here is simply called the collapse random variable, and like this will be our model for data aggregation. For example, we can think of each iteration as some scribe that copies a book from one copy to another.
So these are all the time convex spaces, and these maps are affine.
Yes, every one of F is an affine map, but this first one is necessarily of this type, while these are just affine maps and we cannot say anything about them. And the challenge that we are approaching is to find a way in such a process to counteract the loss and distortion of information. Okay, so it is an important distinction because the information is usually measured by some function, like for example, the Shannon entropy, and the loss of information is identified by the achievement of smaller values of this function, but this is not the only thing that happens along this chain. Here, the data itself can be, in a sense, distorted. To see it more concretely, we would need some formal definition of shape of data and sections like this to embed the shape at the kth step onto the k-1 space and compare how these two are to each other. And not surprisingly, there is a whole branch of mathematics that is written is information geometry. So, okay, I already mentioned the need for information geometry. I mentioned the loss and distortion of information, and it may seem a bit hopeless to retrieve anything of value if at each step we systematically lose. So to counteract it, we need to introduce some replication, which is intuitively quite easy to understand. For example, if you have the experimental data, you can make the same experiment exactly the same independently many times, and this would more or less duplicate your data independently, which should bring you more information that you were losing during the collapse of random variables. And second source of information that should be available for us would be the Bayesian revision, i.e. getting some evidences from somewhere else than doing the same thing again and again. And together, these two that will be formalized as group actions will form a reinforcement group action, which will help us to counteract the systemic loss of information. Okay, so now that we more or less know what we'll be dealing with, let us look at the formal structures that will be necessary for our epistemic machine to make it a mathematical object. So first of all, we will need some probability spaces and functions of reinforcement group on them. This is at the very beginning, at the very first state where we have the probability measures on F before any expected values and any collapse has even happened. Then when we go into the realm of purely convex spaces that are not related with probability spaces directly, then we would jump to convex geometry. And for this geometry to make sense for us, we will today only talk about the convex polyhedron that will be equipped with a stratified and smooth, and for importance targets in geometry. So Riemannian metric that is related to information. That's why there is the Fisher information part. And in the case of synthesis, this will exactly be the Fisher-Rao information metric that you can find in many books. This will come from its convex information potential simply as a Hessian. And moreover, this reinforcement group from probability spaces would be also acting on each of the convex spaces as a legal group. And that's all nice. The morphisms in this convex setting will be nicely connected both ways, just like we saw here. So this will be just surjective affine maps, and these here would be sections of these, but not any sections. They will be isometric, they will be orthogonal, and they would realize the Jennings principle. which is really, really, really nice. And to be quite honest, without James' principle, none of it would work. And to maybe not prove, but suggest that this connection has any mathematical merit, these two structures, the purely probabilistic one and the purely geometric one, would be connected by a functor, and this functor will be deeply intertwined with the Kullback-Leibler divergence. So, okay, what did we manage to get on the geometric side? Well, first of all, the above sections are isometric embeddings of spaces of expected values with information metric. Second of all, the resulting retraction. So going first by F and then by S, we'll land into the same space. And this would yield us a retraction that is orthogonal under the information metric. So basically the best scenario we would like to see. The third one is more or less how the group, this information Lie group action realized. And it is also deeply connected with convex geometry, because going to the random dual coordinate system, we would see that the group action that is first and foremost defined purely probabilistically on probability basis on the simplex of probabilistic measures on finite set, they will appear as the on the one hand translations in the dual variables, and second of all as a gradient of the information potential. And at the very end, I'll say a few things about how these two are intertwined and how, from a certain point of view, they're inseparable. And first of all, the resulting orthogonal retractions mentioned in theorem 2 retract the reinforcement action on the domain of our morphism onto the reinforcement action on its codomain. I would like to spoil something that will come up later, because theorem 4 may suggest that we would get some result on equivariance. Surprisingly, it's just a bit weaker. This relation between these two actions we call sesquivariance, simply because we haven't found it anywhere else. And second of all, equivariance implies sesquivariance, but we'll see that in the details in part 3.
Can you help me imagine this reinforcement action?
Sure. Would you like to imagine it
on some simple example?
Okay. Would you like to imagine it more probabilistically or more geometrically? Geometrically. Okay. So when you simply write for you like entropy, it's something equal to 0 to n of p k times logarithm of pk. Mm-hmm. This will be plus minus up to constant. It's defined by the geometry of the simplex. This function would be your key to everything. Because first of all, if you look at the partial derivatives of it, if you take partial derivative with respect to the k variable, what you will get is the normal logarithm of the k coordinate divided by the zero coordinate. And this is your Legendre dual coordinate. So the Bayesian action would be simply the translation in terms of this, the coordinates. This would be.
So what's the group? R? R.
Yeah, to be wholly precise, the group that manages it would be R n plus 1 greater than 0. Would be the multiplicative group of positive real numbers taken to n plus first power and divided by r equal to 0. Yeah. And this will be one group, and the other one would be the flow.
Just a stupid question. So what's the difference between what you wrote and this multiplicative R positive to the power n?
It's simply that if you want to write your formula directly so it corresponds one-to-one to the probabilistic Bayesian stuff, then this is the one that truly acts. The difference comes from the fact that on the geometric side, you use the affine coordinate on the simplex consisting of n plus 1 points. So you have n affine coordinates. So, and on the probabilistic side, it acts on all the endpoints. Okay, and the other one is the replication action, and it comes from the gradient flow of this Shannon entropy. So it would give you the group also multiplicative, and the action of the whole reinforcement group would be the cross product of that Bayesian one with this simple replication one. And as long as you have, let's say, this information function chosen, you would get simply cross product. But at the very end, I was planning to mention that if you do not choose reference measure, which will appear, I think, in two slides, then you would also get the action of this big group, but you cannot split it into cross product. The act of choosing a reference measure is exactly the thing that splits this group into the cross product of that one and this one. Okay. Where is some of the people on the Zoom also managed to gain something from this. So, okay, let us come back to our probabilistics. On this slide, I hope you managed to read it in the meantime. There are mainly just a few notation quirks. I always denote by M the finite measure and by P the probabilistic measure. And when we look at this part, the most important one, it would later play the role of, let's say, a probabilistic simplex. And this condition here only plays an important role in the case of infinite omega, and it has something to do with the relation between the convex structure on measures, because of course we can take convex combinations of probabilistic measures and again get a probabilistic measure, and it generates a certain preorder, and the preorder generated by the relation of being absolutely continuous with respect to one another. We'll see why it's important in a moment. For now, let us focus on these two here, because this will be the Bayesian groups from the probabilistic point of view. The first one will act on the space of finite measures, and this action will induce the action of the second ones on the probabilistic measures.
Could you write down the action of the M on probabilistic measures in the final step?
I think it would be better if I write it here, simply because I have it here already. And when it comes to the basic actors in the finite sense, if I consists of components, then this will simply be 0 and acting on 0 and compute something here. Here we will get the k factor from the vector space B times the k coordinate from probability, and we have to divide by sum BL times BL from 0 and so on every coordinate, so that it will remain the probabilistic measure. In a moment, we'll see how it is connected with the usual Bayes theorem, but let us come back to our fact. Let me remind you that the space Bn is more or less the non-negative bounded functions, and the assumption that 1 over f is also bounded is more or less technical. This acts on probability measures, on finite measures simply by becoming a density with respect to this measure. First mistake. No, it's not yet because it's not the action. So this one will act on all measures. This one will act on probability measure, and we will define the action on all measures. And thanks to the fact that this projective map, which is simply taking f and dividing it by its by its expected value with respect to probability measure P will yield an action of the group BP with group action induced by this homomorphism. And yeah, what I wanted to say is that the action from all measures will induce the action on probability measures, but on all M will be acted and on probability P will be acted. Okay, so as I said, we simply define the action on all measures by transporting the FU to the measure F being the radon-Nikodym density with respect to mu, and because in PM the group action is given simply by point-wise multiplication, or well, value-wise multiplication almost everywhere, everything here satisfies the group action axioms trivially. And this, as I mentioned before, induces the group action of the P almost everywhere bounded functions with the bounded inverse with expectation, which L1 norm is equal to 1 on the simplex of probability measures that are absolutely continuous with respect to P and whose densities with respect to P are L infinity. Okay, we saw that we have some. We'll see in a moment that this is, in fact, the Bayesian group. And as I mentioned in the geometric setting, we can extend this group action. Well, first, we can extend this group from B to B cross non-negative real numbers with multiplication by considering them as more or less formal.
Non-negative or positive?
Positive, my bad. By treating them similarly to how would you doing differential geometry, but there is this gray area where this would be some kind of measure theoretic tangent tensor, but it's not a one-to-one analogy, so please be careful. But besides that, the multiplication of the cross product, which is the usual one presented in this tensor style like that, would give us an opportunity to extend the action from BP to GP, and this extension begins like this. So the only thing that happens here is that we take probability measure mu, we take its radon-Nikodym derivative, we take it to some non-zero power, we multiply it by f, and that's it. So it is a altogether good measure, and we normalize it by this projective mapping. And now, to interpret what we just did, because we've constructed some formal stuff, but it is even connected to anything that we know. Unfortunately, the usual Bayes theorem for simple finite disjoint sum of hypotheses will give us the interpretation of the group BP of P as the, well, Bayesian action. To see that, we take basis formula and take a look at what happens here. Here we have this quotient, and if we define a function exactly using this quotient, we would see that it will be an L-infinity function on I, satisfying everything so that it belongs to BP of Q, where for Q for simplicity uniform distribution on the finite set. And in fact, if we calculate what happens when such a function acts, oh, right, because it's in here. I should have made a bigger space between those two. If we take the two conditional measures that appear in Bayes' theorem and apply the action formula to them, we see that exactly the result that we get on the left-hand side of classic Bayes' theorem is the result of the action of this F on the measure that appears in it on the right-hand side. That's why we call the action of BP the Bayesian action on the simplex of probability measures. For the other part of our group GP, we need to extend the usual definition of differentiability in probability spaces because it is a bit of a mixture of usual random-Nikodym differentiability of measures and measure disintegration. To put it simply, we take into account two probability spaces. We take a map from one to another, and we demand that it's measurable. Then, going a bit against the usual definition of random-Nikodym differentiability, we define the random-Nikodym differentiability of a map pi instead of differentiability of one measure with respect to another. And we demand that, okay, this random-Nikodym derivative should have values in measures on the domain, just like with the disintegration of a measure. And again, just like in the disintegration of measures, this has to be a measurable map if we feed it with any measurable set. The summary of the value of this random-Nikodym derivative at I on the fibers on the I fiber of pi, And lastly, the integral formula, which really resembles the one from this integration of measure, has to be satisfied. The difference between this integration of measure and this one is simply that we do not demand that these measures have to be probabilistic measures.
Sorry, could you explain this script M of F in this one?
M of F, these are the finite measures on sigma field F or sigma algebra F. Okay. So here you have a map that each point to each point it assigns a measure, and we demand that if you feed it with a set, it has to be measurable, it has to integrate in a certain way, and for its support to lie inside the corresponding fiber. To get from this definition the disintegration of measure, to get right. To get easy equation, put Q equal to the direct image of P, and to get visual random micro put pi equals to identity.
Sorry, just a quick question. Do you assume that pi is surjective or not necessary?
I don't think so. The only thing that is truly necessary is for the direct image of P through pi to be absolutely continuous with respect to Q. The question of surjectivity can be circumvented through the usual Radon-Nikodym derivative, because if you take a look at the measured disintegration, then over there you have more or less surjectivity, because you take the direct image of a measure, so the stuff that is outside the images of measure 0, and you take some measure Q that is, let's say, bigger than this direct image in the sense that it has a larger support. You simply take the Radon-Nikodym derivative of this direct image with respect to pi, and this with respect to Q, and the difference in support will be taken care of by the set of zeros of the usual Radon-Nikodym derivative. I hope that answers your question, Adam.
Thank you. Thank you.
Sure.
Excuse me, I have a question about the definition of Radon-Nikodym differentiability. My question is that are some usual theorem of calculus, for example, the composition of differentiable map or differentiable map, chain rule theorem, or something else? Are they valid in this case? For example, can one say easily that the composition of two differentiable map is differentiable, or there are a lot of other theorem in calculus of differentiable functions? My question is that is it a trivial question to ask such kind of question in this major theoretical setting?
To put it simply, almost not even almost. All the assumptions for differentiability you have to impose are the same as for the measured disintegration, because this is the let's say, heavy lifting part of this generalization. And if you are, well, for example, in the standard Borel spaces, and you have the disintegration, then once this disintegration is fixed, everything else that happens in here is the usual Radon-Nikodym differentiation, and well, then all the usual rules apply. So I would say that first of all, if you want to ask about the rules governing by it, is to take into consideration what rules apply to measured disintegration, and then overlap it with simply exchanging the one measure in here, which happens simply by the usual Radon-Nikodym differentiability. I'm not sure that satisfies you in 100%, but we can talk about it after the talk, because it's a bit of a tangent.
Yes, I see. Thank you.
But what's your answer to the question whether you can compose this condition? Positive? Yeah, okay.
Yeah. As long as you can compose the measured disintegration, it applies one-to-one to this one.
Mm-hmm.
Okay, so now we take a jump into a bit of a dangerous territory, because we will kind of construct a fiber product of probability measures. The kind of part comes from the fact that it won't be, at least we won't check whether or not it's universal in any sense, simply because the conditions on these morphisms would be a bit strange, i.e. we will demand that pi1 and pi2 are Radon-Nikodym differentiable, and then we will be able to define such a big measure. And why I'm so cautious when it comes to stating any categorical thing about this construction. It is simply because the idea to incorporate this extended Radon-Nikodym differentiability appeared really recently, and we haven't checked what is the proper choosing of morphism for it to have categorical properties. But I want to warn you that if you look at the fiber product in probability spaces, then the demand on all these four morphisms would be that the direct image of this measure is this measure, of this measure is this measure, and similarly here. And if this kind of demand on morphism is posed, then this doesn't give us the construction that we are looking for. And we spend a lot of time looking for the error, because theoretically everything should work out splendidly, but instead of getting different measures when we went on the diagonal, just like we did, like we were doing in our intuitive examples, where getting the same measure, and this led us to this definition which uses the extended Radon-Nikodym differentiability. And why did we even do that? Well, thanks to that formula from the previous slide, you are able of constructing the whole sequence starting from omega p. You can take the sequence of fiber powers. If fiber power would be equipped with the fiber power of the measure. And what is the most important part is that taking a direct image from each of the spaces would yield, in general, different measure. If it yields the same, then this is some special property, which is really, really interesting. But by calculating this direct image, we would see that what it does, it takes the derivative with respect to measure Q of the direct image of the starting measure P. It takes the cave power of it and divides, let's say, normalize this measure by dividing by the integral of this, which, well, is simply the action of our multiplicative group. But what is really striking here? Well, the interpretation of each of these spaces. What it does is it takes the events on omega and it replaces it with a copies of the same event, and moreover, these copies are independent from each other. So it can be used to model this intuitive idea of data replication. Okay, so as the last step from this purely probabilistic world that we will need is the idea of two measures being equivalent. Well, it simply means that one is absolutely continuous with respect to the other and the other way around. Plus here we, by writing this instead of simply these two inequalities for absolute continuity, we also impose the condition that the respective Radon-Nikodym derivatives have to be L infinity. And at the very end, we can now define the so-called Hilbert-Leibniz divergence, which takes two arguments. One needs to be absolutely continuous with respect to the so-called reference measure. The other is what we call the reference measure, and it takes non-negative values. It's simply defined by this formula, and it may not look like that, but for some of you, it may remind you of the maximum likelihood methods from statistics, and it's not a coincidence, but this is not the direction that we are going to go. Okay, one quick thing about the replication, which was motivated from here and realized through this action. Well, this gives us the whole process on the probability measures on the codomain of I, and it has a remarkable properties, i.e., I'd like to explain that it should be the fixed points of this process that should be defined as uniform distributions, because the usual knowledge says that, okay, if we want to have something that we could call a uniform distribution, we would need some group action that smears the probability equally throughout the space, which leads us to Haar measures that if the group is compact, then okay, this Haar measure can be normalized. We could get a probability measure that everything works out. If not, if it's locally compact, then the so-called amenability theory enters, and it provides us with some ways of studying the means, which are the generalized invariant integrals.
Could you explain this uniformity on the example of
or the examples are right here. If you want a different example, no worries, I can provide with you. I wanted to go with two classic ones. One is the Gaussian one-dimensional distribution. If you take the ELF replication of this measure, you will simply get such a Gaussian density. And if you another mistake, you should be L. You should be L. If you take it like that, then if you go with L to infinity, it would destroy your variance, i.e. the variance would go to 0 and you will get the Dirac delta focused on the mean M, and you would get, well, the Dirac delta at M, which as a one-point distribution is of course uniform. On the other hand, if you go with L to 0 and you smear, maybe not smear, you prolong this Gaussian so that it more and more and more looks like the straight line for the most of it, and then somewhere really far it goes to 0, then intuitively it should go to some invariant measurement. Yes, in fact, if you take the limit in appropriate topology, you would get a distance to an invariant mean on R. And these are two nice examples. But okay, in one you have one point set, so the trivial group is the Haar group that acts on it, and in the other you have the action of R. So both of them are the uniform distributions in the sense of Haar measures. But if you take the arbitrary set of finite level, then you would get the measure of this density is simply the characteristic function of this set divided by this set. It gives us, of course, a probability measure. And if you replicate it on and on, it will not change. And because it will not change, it is a fixed point of the replication process. And maybe it's just me, but if you take, for example, some fat Cantor set, I am unable to show which compact group acts on it freely and transitively to state that yes, it is a uniform distribution in the sense of action of inheriting R measure from some set. And even if I could, this argument is just one line and not some weird construction of something I can't even imagine. So this was just a bit of propaganda. If you're not satisfied, I can.
Oh, I'm satisfied, but you started with difficult examples.
Oh, sorry.
We did the final case.
Yes, sorry. For the finite case, I think I'll come back to it in a moment when we'll go to the geometric realm, because as the last thing that bridges probability and geometry, I was mentioning that the set of probability measures is a convex set. And I also mentioned that the relation of being absolutely continuous is a preorder. And, well, the convex structure also provides us with certain preorder, which is, to put it simply, the preorder of possibly lying in between, i.e. the x2 is called bigger or equal than x1 if there exists some point y such that x2 is the inner point of the interval connecting y with x1. It is only a preorder. Is reflexive trivially, and thanks to the identity on how the convex combination parameters change when you exchange the parentheses, it shows us that this will also be transitive.
So you could write an explicit formula for this arrow with a sign T.
Yeah.
Sorry, I'm a little bit confused about this notation. So this T is open interval or closed interval?
I'm confused.
Y
1 minus T times
T
Y plus
x1 is equal to 1 minus T y plus T x1. It's the usual convex combination, nothing special.
Sorry, I have a question. Could you
Yeah.
Yeah, so I'm a little bit confused by this notation. So this T should belong to the open interval or to the closed interval?
It says closed.
In the definition
of this operation.
Closed, in the definition of the relation, the open. Because, for example, if you take just a 0-1 interval, you want each point in this interval to be bigger than both 0 and 1, but you don't really want 1 to be bigger than anything and 0 not to be bigger than anything. And in particular, you would not want 0 and 1 to be comparable at all. That's why in the definition of the preorder, you have the open interval. And that's why for reflexivity, you have that you take the interval which, well, all lies in the point.
Every T works.
Yep. Well, except 0 and 1.
Okay, I see. Okay, so both endpoints are the same x. Okay, I see.
Yeah.
Uh-huh.
Exactly. So you don't take the x at the beginning or the x at the end. You take the x in the middle, but it's a degenerate path.
Sorry, may I comment, please? Adam, if you look at this second equation, which means associativity of this convex combination, you see the parameter, which is a rational function of T and S.
Yes.
If T and S are both 1, for instance, look, you obtain the 0 in the denominator.
Yeah.
Okay? So this would create a problem with extending to the full interval from 0 to 1, for instance.
Okay, so the larger the element, the more it lies in the middle of the segment, yes? Is it right to think about it?
Yeah, if you think, let's say, two-dimensionally, the points in the interior of the triangle are bigger than everything. The points that are on the sides of the triangle, they are strictly smaller than the ones in the interior, but they are strictly bigger than the vertices. And the vertices are the minimal points.
And sorry, how about points? All points in the interior are non-comparable?
No, all points in the interior are equivalent.
Equivalent.
This is why this is a pre-order. It's quite easy to see, because if you take a triangle and take 1 point here and 1 point here, then we can take a bit bigger interval. And let's say that it comes through both these points. You take 1 point here, well, for example, 1 point here, and you get one interval that states that the one on the left is bigger than the one on the right. Well, I'm talking about only black points. And using the other one, it's the other way around. I'm talking about it because this gives us a pre-order structure on measures, and the absolute continuity gives us another pre-order. And everywhere else I demanded that the Radon-Nikodym derivative is infinity, simply because under this assumption, these two relations are equivalent. And this enables me to give this probabilistic simplex a certain combinatorial topology called Alexandrov topology, and then build on it some sheaves, take sections of sheaves. I was planning to talk about it at the end, but I have to hurry up because the time is catching up with me massively.
So this is a little bit like simplicial complexes, yeah?
Yeah.
Okay.
Okay, may I go on, Nathan?
Yeah, he disconnected. So
Yes, of course.
Okay, great. So I thought.
And what does it mean, absolute?
So there are quite a few of them. Okay, either way, the stuff from before could enable me to give these simplices some combinatorial topology, which would be useful in the so-called invariant case. But now I'll try to, in 20 minutes, rush through the convex geometry part of my talk. So because we want to use tools from Riemannian geometry, we need not some combinatorial topology, but the topology on simplices and convex sets that is inherited from Euclidean spaces. That's why from now on we will restrict to finite probability spaces. Okay, so as we've mentioned in the problem description, we will consider convex sets with information potentials, which are stratified smooth, strictly convex functions. And the morphisms between such spaces would be the surjective affine maps that satisfy the James principle, which is the main reason that everything in here works. Oh, okay. If you remember, a few minutes before, we defined the Kullback-Leibler divergence in terms of an integral from a logarithm of Rayleigh-Nikodym derivative, and because we are on the finite space, we can treat each probability measure as simply the simplest. So the direct image pi is defined on the vertices, but the direct image is defined on the measures on the vertices. So it goes from one simplex to another. And the Kullback-Leibler divergence acts properly in the sense that it satisfies the James principle in such a form, which enables us to treat Kullback-Leibler divergence as a functor from probability spaces to such information objects, where here we have convex sets and here these so-called information potentials. And the fact that this formula gives us a functor is directly a consequence of the fact from the last page.
Covariant.
Covariant, yes. The problem that we've encountered before was that everyone would like to have in here, instead of Kullback-Leibler divergence, to have Shannon neck entropy, simply because it is more canonical. There is a functional equation that is determined wholly by the geometry of simplex, which determines the Shannon neck entropy up to a constant multiplicative constant, no, additive constant. Multiplicative constant, my bad. Okay, so it determines it up to a constant, but it's not functorial. When you put it by James principle, even if you have here a uniform distribution, which would give you Shannon neck entropy, here you have the direct image, which may not be a uniform distribution, so it would not yield you the Shannon neck entropy. That's why we had to deal with the Kullback-Leibler divergence, but fortunately, the measures that we are getting would be equivalent to some uniform distribution, and thanks to that, the difference between what we get on the right-hand side here and the Shannon neck entropy, which we would like to have, is simply a difference of an addition of an affine function. So this Kullback-Leibler thing minus the Shannon negentropy is just an affine function, and it has quite a few positives. But
could you elaborate on morphisms?
yeah,
Just recall what the morphisms are in these two categories.
the morphism that I'm considering in probability spaces in this context are the ones that preserve probability, i.e. the morphism between omega and p and sigma G and Q are the measurable maps of FG measurables from omega to sigma, such that the direct image of P is the direct image of Q.
Direct image of P is Q, or what do you mean that?
Yes. To be quite honest, now I have to think carefully, because there are two situations which we consider. For one, the morphisms are as above, and for the other, they are as below. Here I take the both ones, because corresponding to this, on the convex set, I only limit myself to affine maps that are surjective, and the information potentials satisfying the James principle. And when you put it like that, then it is a covariant factor.
Okay, and now the codomain. So
yes, the codomain.
What are these information objects one more time?
Convex.
Okay.
So
we'll have some
convex set. You have affine, and we demand that they are surjective. And
okay.
Here you have the stratified smooth, strictly convex map. And on them, we demand to satisfy James principle. And exactly this states that when we use the morphism from set from 0 to n to the set from 0 to n, then the Kullback-Leibler is the covariant, it satisfies the James principle, just like the covariant factor applied to the map P should. Okay.
That's whose theorem? That's your theorem?
I would say that it's mostly my supervisors, because I did more of our work when it comes to the probabilistic side, and he did more when it comes to geometric side.
It's pretty nice.
Okay. This calculation was advertised to everybody to perform because it's not present in the literature.
Yeah.
It's a very simple thing. It was not observed by probabilists, by statisticians.
I was more surprised by your observation that in the literature it's impossible to find that that Bayesian theorem leads to group action, but that's besides the point. So let's go through this stuff again, as I mentioned, because Shannon entropy is defined as the Kullback-Leibler with respect to uniform distribution. Again,
delta K is missing.
Yeah, delta K is missing. This was our approach at the very beginning, and we were happy because everything worked out. But the moment we looked for functoriality, everything collapsed. But thankfully, Kullback-Leibler managed.
Okay, and why did you look for functoriality?
if
In simple examples, analogy between this probabilistic side and this convex side was striking. So it's a natural conjecture.
yeah,
These things must be related.
to be quite honest, if I gave a talk about some convex stuff and some probability stuff and could not say that these are connected functorially, I don't think many people would see this connection as meaningful. At the moment you say that this dependence is functorial, everything's okay. That means you've encountered something important. So, okay, thanks to the James principle, we can define the sections of each morphism F. So coming to the one of the beginning slides where you had the chain with maps from left to right going FFFF, and then
You are surjective here.
yeah, the F's are surjective and S's are the sections of F. So the existence of those S's that were written in this diagram at the beginning are exactly thanks to the James principle here. And moreover, these sections behave unbelievably well, because if we take these information potentials on the domain codomain, if this section preserves the potential which the one constructed from James principle does, then it also preserves the Riemannian metrics coming from the Hessian of information potential. So it preserves the Fischer-Rao information metric. And
so why this theorem is not trivial? Because since G is a question of the information potential, such implication would be fulfilled for free for a fine matrix S. It is reality, complete reality. But the point is that S is not an affine function. So the fact that it is an isometry is right.
It's higher here because you can catch something like this. And how does this interval lie inside this triangle? And you can get that it lies somewhat like this. And this S take this interval onto this curve. And not only is it an isometry, the projection onto it is orthogonal, and the actions that we defined in purely probabilistic terms can be defined in purely geometric terms. I mentioned it some time ago when you asked for some intuition. So yeah, the Bayesian action is that it induced from probability space onto this convex simplex is simply the translation in dual coordinates, and the simple replication comes from the flow of the gradient of negative entropy function. This is where the fact that difference of values of two Kullback-Leibler function taken for different right arguments, so for different reference measure, is an affine map, which means that even though we only can get the gradient of some Kullback-Leibler function and not Shannon entropy, when we pair it up with Bayesian action, the vector fields generating both these actions which generate the big group action. And inside this group action, you would have this replication action. Because when this difference is affine, this simply means that the replication action is shifted a bit by translation. So acting via translations, you can untangle it, but how to do it in practice is not obvious and not trivial. So because I'm running out of time, I'll try to finish this geometric portion. So because we only get access to this image of this section S, so to this red curve instead of the whole triangle, we could ask, okay, we have this geometric axis on the triangle, we have the geometric action on the interval. What happens with the geometric action on this red curve? And well, this action is not equivariant, but it is equivariant. And when we have the action of H on X and G on Y, the homomorphism from G to H, we say that G and H act equivariantly if and only if such a diagram commutes. It's a formal definition and...
May I repeat?
Sure.
So this would be read in the following way. So we have a pair Fs, and we call such an Fs given this homomorphic phi and these two actions equivariant.
Okay, so
so it's a property not about the action, it's about the property of the mapping between two actions.
Okay.
So you know equivariance.
What? Phi is just a group homomorphism.
Yes.
And F is what?
The pair F S is the pair of a defined map.
Okay, so F is repeating.
Yes.
Of F, okay. Okay.
So this is regarded to be a morphism between X and Y.
Yes.
And this morphism is equivariant with respect to these actions.
Yes.
If this diagram commutes. Okay.
S is X to Y, phi is H to G.
So this is an extension of equivariance.
here is the simple observation why the extension, because it says equivariance will be written in such a way, and when F is a starjection and F is equivariant, then from here you would get that phi of H acts on F composed with S composed with F, and by associativity of oh my god, I lost the word of composition. You would simply exchange the parentheses and get identity, which yields here. Okay, and the last of these geometric theorems is that when we have our information objects, which we manage to equate on the way with the network and the group actions, and F is a morphism between them. Because it's a morphism, it has this section given by Jane's principle. We can check whether or not these actions are related by equivariancy. And in fact, they are. Okay, I am literally on time, but we started 40 seconds later, so I'll borrow a minute. So what are our future prospects? One is to go beyond the finite probability spaces when it comes to the geometric side, and there are two roads that can be taken. One is to look throughout the functional analysis for topologies which would fit nicely to our picture, so that, for example, all the limits of replication action would be realized as true limits in this topology, or we could treat this dynamical system as fundamental. The other way forward is to change the probabilistic side from the classical one to one of the non-commutative frameworks and do similar things, but not taking as our reference point the Shannon entropy, but the von Neumann entropy. So basically, the reference model here would be the trace would play a role of reference measure here, and we would check what changes when we change the trace. The positive side of this is that even though the probability side of this changes dramatically, the geometric side doesn't change at all. And the last one is to try and divorce ourselves from this a bit arbitrary choosing of reference measure. So instead of calculating fullback library directly for some chosen measure P, we could divide everything and treat it as something that depends only on the absolute continuity class of P, and this would yield for us some invariant theory. We made a few steps along this line. For example, the probabilistic group can be defined without choosing the reference measure. And for the geometric part, instead of simply having a convex set with information potential, we would need some sheaf. We would need some sheaf with some combinatorial topology. And our basic object would be the convex set treated as a preorder with a global section of this sheaf, but it is something for part 2, which I hope to refer either next year or in 2 years at the latest. And thank you very much. Sorry for going over time.
Thank you. Okie dokie. Any further questions? Adam?
Yeah, maybe half a question and half a comment. Since this notion of von Neumann entropy is the one particular way to get something which is of, in general, von Neumann algebras of a kind of a non-commutative probability, but also there is this type 2 factor. So maybe this would be some direction which could be somehow investigated. I don't know. Finite von Neumann algebra in general, or maybe more specifically 2 factor.
Yeah, so thank you, Adam. To be quite honest, the world of non-commutative probability is so wide that I personally have no idea which framework to use to yield something fruitful. So I think we'll first manage to finish the third bullet, the invariant theory, and then we'll take a look at the non-commutative probability side. But be sure that I'll contact you for some tips when it comes to von Neumann algebra.
So that was your comment.
Yeah.
And how about the question?
No, it was half a question and half a comment.
Okay. Anybody else on the Zoom? Dimitris? Oh. Since the people are happy on Zoom. You guys? Okay, I think it's time for ramen. So let's thank ŁUKASZ here. Let me stop recording.